This next example is very important. Let's consider the infinite sum starting at n equals 0 and going to infinity of, let's say, k to the n power divided by n factorial, or n if you want to be snarky about it. N with an exclamation point. It's called n factorial. K is a constant. N is the variable for this summation. I'd like to know, does this series converge or not? And in chapter 10, we're even going to figure out what it converges to. And maybe I'll even have Mathematica do it for us today, because it's kind of interesting to see what it converges to. It does converge to something that's actually computable. But what is n factorial? If n is greater than or equal to 1, n factorial is n times n minus 1 times n minus 2 times n minus 3, etc., dot, 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 down to 3 times 2 times 1. If n is greater than or equal to 1. So, for example, 4 factorial is 4 times 3 times 2 times 1 is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, which turns out to be 120. Factorials grow big fast. 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 10 factorial is 3,628,800. I could also do that by going to my math menu to probability, and there's an exclamation point. Whoops. 10 math. Go down to the exclamation point and do it that way too. 50 factorial is very, very big. 3 times 10 to the 64th. Okay, factorials grow very big, very rapidly. So the bottom of the fraction is going very big, very, very rapidly. I'm starting out at 0, though. So evidently I have to divide by 0 factorial. Yes, you want it to equal 1 if n is 0. 0 factorial by definition is 1. In part so that this works nicely. And in part so that other things in math work nicely. There's no deep reason for this other than making formulas work out nicely. Okay, it makes sense by patterns in certain formulas to define 0 factorial to be 1. K is a constant. If I write this out the long way, so I get k to the 0 over 0 factorial plus k to the first over 1 factorial plus k squared over 2 factorial plus k cubed over 3 factorial, etc. If I want to simplify that a little bit, k to the 0 is 1, 0 factorial is 1. The first term simplifies to 1. Second term simplifies to k. Then 1 over 2 factorial is 1/2. 1 over 3 factorial is 1/6. 1 over 4 factorial is 1/24, etc. Does this converge or diverge? It should be not clear. Why not clear? Because these terms, it's not clear what's happening to them as n gets large. Why not? Because both the top and the bottom, especially if k is bigger than 1, could be getting pretty big as n gets bigger, right? If k is 10, if n is 10, I get 10 to the 10th on top. 10 billion. Divided by 10 factorial, which is 3 million something. If 10 is 20, if n is 20, I got 10 to the 20th up here. What is that? I saw quintillion or hextillion or something like that. Divided by 20 factorial. Is that bigger or smaller than 10 to the 20th? It's not so clear. So it's not clear what's happening to these fractions, but here's what is happening. Factorials in the long run, no matter how big k is, do go to infinity faster than k to the n does, making the fraction go to 0, in fact, ultimately pretty rapidly. And the series does converge. But to prove convergence, we do not use integral test, because we don't want to try to integrate something like that with respect to x in place of n. And there's nothing really to compare it to, so we can't really use the comparison test. We need a new test. It's called the ratio test. For a series, notice the summation sign. Series means summation sign. Infinite sum, really. For such a series of AN, suppose the sequence, notice that's the word sequence, not series, that looks like that, sequence of ratios, that's why it's called the ratio test, has a limit, L. If that limit happens to be less than 1, then the series converges. If it's bigger than 1 or infinite, then the series diverges. And if that limit L equals 1, well, the test is no help. The series might converge, it might diverge. You have to try some other test. You might also wonder what happens when the limit doesn't exist. It's more complicated. When the limit doesn't exist, there's actually some situations where the series converges and some where it diverges. It's a more complicated kind of test when the limit doesn't exist. All right, so how is this useful? We want to use it for this example where this is the AN right there. That's AN. So we have to compute these ratios. Absolute value of AN plus 1 over absolute value of AN, and see if the resulting ratios have a limit L or not, and what L is. So let's see if we can do that. That's my AN. Therefore, what is the absolute value of AN plus 1 over the absolute value of AN? K is a constant. N is the variable. With AN plus 1, it's just like plugging N plus 1 into a function. In the formula for AN, replace N with N plus 1. That's what you do. So I get K to the N plus 1 over N plus 1 factorial. With the absolute value of AN itself, I get K to the N over N factorial. But this still seems kind of complicated. How do you deal with these absolute values? And fractions within fractions. And factorials. Ugh. Well, okay, keep in mind the factorials themselves are not negative. So I don't need absolute value signs around those things. Also, the K could be positive or negative, but the N and N plus 1 are not. It turns out I can put absolute value signs just around the K's. Like this. Because everything else is positive. And then I'm dividing two fractions. Remember back to 4th or 5th grade. That's the same as multiplying by the reciprocal of the fraction you're dividing by. It's just all symbolic here instead of with ordinary numbers. That's better. It gets even better when you realize N plus 1 factorial. Well, that's N plus 1 times N minus 1 times N minus 2 times N minus 3, blah, 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 blah. If you think about it carefully, it's really N plus 1 times N factorial. And the N factorials cancel. Something else nice happens. This is the same as the absolute value of K to the N times the absolute value of K to the first. And the absolute value of the K to the N's cancel. Leaving you with a simplified expression, the absolute value of K to the first, which is just the absolute value of K, divided by N plus 1. That is what this thing simplifies to. What do you do now? We want to know what is the limit of this thing as N goes to infinity. K is fixed. Got a fixed number over N plus 1. This sequence, not series, this sequence converges to 0 as N goes to infinity. And that's my L. And that is less than 1. Therefore, by the ratio test, the series in question with a summation sign converges. And it doesn't matter what K is. Doesn't matter how big K is. K could be a Google and it still converges. It could be a Google factorial and it still converges. It could be a Google factorial, a Google times to the Googleplex power, and it still converges. Because n is going to infinity and factorials grow faster than powers. What does it converge to? Our last thing of the day. Mathematica, let me know. Will you, please? Converges to, drum roll, e to the k. Surprising. Amazing. E. Popping up unexpectedly. Or is it unexpected? If you know math well enough, it's not unexpected. We'll learn enough math that you'll come back to this later and say, I knew that had to happen.